So this video and the practice problems that go along with it are the heart and soul of the equilibrium unit. So even if you don't need to watch the videos for some of the other practice problems, make sure you do for this. So the equilibrium constant is our ratio of products to reactants. It tells us how much, relatively speaking, of each different chemical do we have once we reach equilibrium, and we have that reversible process going at the same rate in both directions. Because we're not totally consuming our reactants and turning them into products, we don't react until something is zero and something else makes as much as possible. We have to take the information we know about that reaction, our equilibrium constant, to be able to think about and figure out how much of each chemical do I have, relatively speaking, and then specifically, what is the molarity or the pressure of each of my chemicals. That's when and how we use the equilibrium constant. And as you're solving these problems, and it will continue into the acid-base unit, you set up a table that's either referred to as a rice table, that's what I prefer, or an ice table. I like the R because it's important to remember that we need to look at the balanced reaction. So the R in rice table means we rewrite the reaction. It's already going to be there for you in the either multiple choice or free response question. So you could just set this up below the reaction. The next column is the row is initial I. That means, what do I know that I started with? Did I start with a certain amount of reactants, a certain amount of product, a certain amount of everything? Or maybe that's the thing that I don't know. C is change. This is where stoichiometry comes in. Even though we're not going to go into completion, the coefficients play into how quickly a chemical is consumed or made. And I said chemical rather than reactant or product because we could have enough products that those are being consumed and turned into reactants, or we could be consuming reactants to turn them into products. But one side of the reaction is decreasing in amount, the other side is increasing amount, and it happens based on the coefficients. And then the E stands for equilibrium, kind of the point of all of this, which is when I get to equilibrium, how much of everything do I have? And there's a good example of a rice table here with a fairly simple reaction. Nitrogen monoxide breaks down into nitrogen and oxygen, the opposite of what we looked at with our red and blue reaction from a little while ago. So if it says I put some NO in, maybe this reaction would say I start with 0.2 molar NO, or I charge a flask. That's a phrase that's used sometimes. That just means that's how much we put in. That would be an initial amount. If it doesn't tell us how much nitrogen or oxygen we have, we assume that we have none of that, or those are starting at zero. The thing that I don't have any of, I am creating some of that, so that is plus a certain amount. The thing that I do have is being consumed, so that's minus a certain amount. And the X, we say across the board, but then we connect that to the coefficient. Because to make every nitrogen molecule, there's two N's there, so I need to consume two NOs. So based upon that coefficient, I've got a minus 2x, a plus x, and a plus x. The equilibrium row is once I get to equilibrium, what will the concentration of each of these things be? Sometimes it's a numeric value that we're given and we can plug directly in. Sometimes it's going to be solved for in terms of x. So here I know I had 0.2 and 2x of it went away. Here I don't know how much, or I started with none. I end with a certain amount, but I don't know how much. And by being given other information, usually specifically the K value, we can solve for what those X's are. So once you've got your rice table set up, you are writing everything that you know in there. You're paying close attention to your coefficients for the change row. You're figuring out what you know and what you don't. You have to set up your K equilibrium expression. And then if you've got the number, you recognize that that ratio is equal to a certain number. Sometimes you're not given the number and that's what you're solving for. Sometimes it is. And often in an AP free response, writing the equilibrium expression is a separate part. But you may see some equilibrium in multiple choice and not kind of be walked through the process. So it's important. Rice table, equilibrium expression. If you are given values, they could be moles, grams, liters. but we want them to be molarities. If it's a KC, we want them to be usually atmospheres if it's a KP. But beyond that, we have to figure out, is that how much started the reaction, or are they telling me once I get to equilibrium, I have that amount? In either case, we would plug it into the correct part of the table. If you're given the K value, you solve for X. If you're given an X, you can solve for K values. So in this instance, we would have to be given one more number, either what X is equal or what K is equal, to finish and solve that problem. This will come up a few times in the equilibrium unit, but way more in the acid-base unit. If your K is very, very, very small, that impacts the way that we do our math, and some of the solubility later in this unit will have that. For right now, don't worry about that too much. But what does happen here is sometimes you get into some nasty looking equations when you've got X's on top and exponents and X's on bottom and exponents and your K, and you're trying to solve for all of that. The good thing on the AP exam, so the good thing that the College Board kind of promises us, is that the problems will never involve the quadratic equation. You do not have to solve in terms of the quadratic equation. There's some other way to simplify it, or there's something about the way that you've written the problem where you've left the number out. So you'll see some examples of that in the 4 practice problems, where even though something looks like it's fairly difficult, it may not be as hard. Just so you know, one of the practice problems that I give does require the quadratic equation, and you might see some of that in other practice problems, online homework, etc., because equilibrium is a huge part of first-year chemistry in college, and solving for things with the quadratic equation or an equation solver is something you could be required to do at that level. If I have an error here, or not 0, if your initial concentrations of everything, if there's something that's not 0, meaning we have chemicals or we have a certain amount of all of our chemicals, we may not know if we're at equilibrium or not, and we definitely don't know which way we need to shift to get to equilibrium. Do we already have the right ratio, or is the ratio that we have incorrect? In that case, before you can do your plus and minus x's here, we would have to think about what needs to be consumed and what needs to be made. And we can only do that by, or know that by doing a Q. So you calculate your Q, you determine the which way the reaction would proceed, and then we would know what to add or subtract. Up here, for example, we see that there is no nitrogen, therefore it can't be consumed and had to be added. But if all of these were 0.2, then that means we have some of everything. We would need to compare the amount that we currently have to the amount that we should have at equilibrium to see which side needs to go up and which side needs to go down, because either side could be the plus or the minus. And you'll see in the practice problems a little bit of all of that. So maybe the previous practice problems you just checked answers on, these are going to be really valuable ones to watch the videos. Equilibrium calculations, solving for X, solving for K is a huge thing, and it's totally new. So take the practice, look at the examples, and make sure you really understand how to do that.